So let's just quickly review what we sort of talked about yesterday. You guys can get your notes out from yesterday as I'm going through this. Remember, we talked about Kepler. Kepler was the guy that was really good mathematician. Newton based some of his work on Kepler. There he is there. He was not the gold-nosed guy. The gold-nosed guy was Tycho Brahe. Kepler said that planets move in elliptical orbits, the sun at one focus. Remember that it's really not that elliptical, it's almost circular.
So we'll do the other focus.
What's there?
Yeah.
That's sort of a mystery. They don't sort of know why they move in ellipse, I think. I could be wrong. Yeah. We learned that a line joining the sun and a planet sweeps out equal areas in equal times, which is sort of an odd thing to study. Right? Okay, so we've got a line joining the sun and the planet that sweeps out equal areas in equal times, and that led us to realize that it's going faster when it's near the sun and slower when it's farther away, right? And they talk about that sometimes. They talked about how, like, you know how the moon, when they had that super moon there a couple months ago, right? Did you know about that? The moon was actually closer to the Earth at that time, and it was full, and so it appeared bigger. I think like 13% bigger in the sky. So the moon also moves in ellipse around the Earth, kind of thing, and it travels faster at certain times too. Okay. So the following ratio is the same for all planets or satellites which orbit around the same central body. This was Kepler's third law that says that r cubed over t squared is the same for everything that orbits something, right? Where r is the radius of orbit, either in meters or astronomical units. T is the period. And 1 AU is the average radius of the Earth orbit, 1.49 times 10 to the 11. Okay. Now, r cubed over t squared for things that orbit the Earth is different than r cubed over t squared for things that orbit the sun. Okay, and the constant, the Kepler constant for the sun, the r cubed over t squared value was 3.35 times 10 to the 18 cubic meters per second squared. What exciting. All right. And then I think we got into these sample questions. This is the one that we talked about briefly yesterday. It asked how fast in square meters per second is an area being swept out by a line joining the Earth and Sun. We, for this one, assumed that the area was a circle, which is why we used pi r squared. And the radius of the Earth's orbit is 1.49 times 10^11. The period here, this is 365.25 days times 24 hours times 60, giving us 3.16 times 10 to the 7 seconds. So you get this big crazy number that really doesn't mean anything. All right, so here's sample number 2, which is where we left off. So I'll pause here and let you jot that down. All right, so we've got the period of revolution. We want to find the radius of the Earth planet's orbit. We're going to use Kepler's constant again. We're going to say that k sun is equal to r cubed over t squared. Because this mystery planet orbits our sun, it has the same k sun value as before, that 3.35 number. Oh, I got the whole thing there. 3.35 times 10 to the 18 is equal to r cubed over t squared. Basically, this is can you handle scientific notation and squaring and whatnot on your graphic calculator, on your calculator. You'll need to be able to do cube roots. I hope you know how to do that on your calculator. We should maybe take a moment just to make sure that you're able to do that. If you were so inclined to look up that it was Mercury, you could get that from the radius of orbit, 5.79 times 10 to the 10. All right, here's the last one. This one here says Mars has a radius of orbit of 1.52 astronomical units. That means that it's 1.52 times the distance from the sun as Earth. It revolves around the sun once every 690 days. So if we were to put a colony on Mars, we would have to get used to some really long years. 690 days. Presuming that if we were to set up an artificial habitat on Mars, we would probably have some type of way to...
Every 2 years per year.
Well, we would have a season. I mean, who knows? There would be no seasons, really, would there? Right? Would we artificially create seasons? Probably not. Would people live longer because the years are longer? No. This period is 690. If Venus has an orbital radius of 0.72 astronomical units, how long does it take Venus to go around the sun? What'd you get, Stefan?
Yeah, I got 326.8.
Ooh.
Oh, we didn't use the R cubed over T squared.
Damn you, I hear
This is teaching. Good teaching is force the kid to make a mistake and then throw them the error into it.
No, that's bad teaching.
No.
They should not ever make mistakes.
Come on. All right, so that makes sense. Why does this work? It's because, I mean, you could also, if you want, you could go K sun is equal to R cubed over T squared. Sorry, I wrote that backwards. R cubed over T squared. You could do it that way and then do K sun equals R cubed over T squared for the other one. But you could just sort of set it up. What I've really said here is that K sun of one is equal to K sun of the other, to sort of put them together. Okay? So, who else has a test today? Anyone? You guys do too? Okay. So, I will give you this time.
Oh, I have a test today.
Okay, I'll give you this time to work on those Kepler's laws problems that I've given you. Tomorrow I'm going to do a whack more on satellites and whatnot. We got to talk about black holes. We got to talk about escape velocity and that kind of thing. It's looking pretty good that I can give you maybe 1 or 2 days at the end as sort of a time to get yourself ready for the exam.
So you are the teacher who give reviews, you just give tests, right?
Correct. Now, having said that, I have some tests to get back to you actually.